As we said earlier, with this compression test, we can get two pieces of information from this material. Concrete, can be mortar. That is one, the compressive strength, and that is the maximum load that can be applied to this specimen axially in compression. And from this load, by dividing that by the cross-sectional area, we would then get the stress at which failure occurs. Right? So as long as we know the maximum load that was applied to this cylinder, we can find out what was the compressive strength. Of course, we would like to see more, and that is, of course, the modulus. And if possible, we would also like to see the load versus deformation plot or the stress-strain behavior of concrete. So not only do we want information about the load, but we want to document at the same time how the specimen deforms. So in compression, of course, it would get shorter, right? So in order to do that, we have this device that is sitting around the specimen. Basically, it is 4 blades, so it's 2 pairs of equipment, one on the right-hand side, one on the left-hand side. We want to see the average deformation of that specimen, not just on one side, but on 2 sides. So what we are measuring right here is the deformation of the upper blade and the lower blade with respect to each other. So we are seeing how much does this specimen squeeze as we are applying the load. We typically take off this device at about 70% of the maximum expected load because we don't want it to get damaged as this specimen is crushing. Right? Once we have reached the compressive strength, the specimen typically deforms very quickly and violently, so we have a sudden failure, a crushing. And we don't want the measurement device to be damaged in that process. So therefore, what we typically do is we take one cylinder without any measurement equipment attached to it. We test it in the machine to get some idea what is the maximum load that we can expect. Then in the next specimen, we apply this device and leave it on up to about 70% of that maximum load that we have measured before. Then we stop the test, take the device off, and we continue the test. Ideally, we would like to leave it on and measure the entire load deflection curve to get an idea about the stress-strain behavior. If you design with concrete, in reinforced concrete, for example, it is very important that you have an idea about the complete shape of the load deformation behavior. The stress-strain curve must be known. As you hopefully remember, right, we are utilizing the concrete in reinforced concrete members up to a compressive strain of about 0.0035. The maximum load typically occurs at a strain of 0.001. So 1/3 of the maximum usable deformation according to Eurocode. So we would like to know what is the response of this concrete as we are taking it to a deformation of 0.0035. Okay? With this device, it's not so easy because we don't want to damage it, but there are other ways of measuring the displacements that are much safer, are not harmful to the equipment, and with that we obtain that. For now, what we would like to do is get, of course, information on the compressive strength, but also on the elastic modulus, right? For deformation calculations, if you had to predict, for example, the deflections of a floor panel or of any kind of beam, you need to know what is the Young's modulus of the material. And with this methodology that I just described, we can obtain that information. Okay? So I'm going to hand it over now to Christian, our technician, and he will explain to you how to set up the data acquisition system and then to install the specimen and run the test.
How many specimens?
Just this one for now. Yeah. And then each group will test one or two.
Yeah. This thing works in this way that you have two metal tongues, one on each of these ones that are equipped with strain gauges under this cover. So that gives you a signal from each of these that are here made into one, combined into one signal that is the average of these two. And they have a stroke of plus minus 2.5 millimeters. We are only using minus side, of course, to this because we are doing a compressive test. But you put it on like this, and it opens here, so that when we are going to, since we are going to take it off sometime during the test, you need to put the wires, the cables like this, so you can open it here and take the whole device off like this. And then we are going to measure. This one is a bit difficult to see for everybody. But you have set up the logger to measure now. Yeah. And we are measuring on these 2-3 channels here. The first channel is the load signal from the testing machine. You can see the sensitivity on this marker up there, on this label. And the second channel is the displacement, the combined signal from these two. And the last one is the supply voltage, this one. Since these ones are passive gauges, so to speak, you need to, they are fed by approximately 5 volts supply voltage from this machine out through the wires, and the signal comes back. The signal will be somewhere around from 0 to plus minus 18 millivolts. But since it's a Whetstone bridge, 4 strain gauges, the output signal depends on the supply voltage. And that is why we need to measure the supply voltage also. And we need to do a calibration, by the way, also, because that would be some abstract millivolt signal you get out. And in order to calculate that back to millimeters, we need to do the calibration. You have already done that, right? So you can eventually show that when but we can do the first test and then do the calibration, I think. Wouldn't that be an idea? So we can start the data logger just to see the signals. We have, let's go back to this one, no, this one. Supply voltage is around 5 volts, and the displacement, we can see that it varies from 0 to minus 18 millivolts and plus around 18 millivolts. So it works as it's supposed to. And on this screen we can see some curves. The red one being the load and the green being the displacement from these two. So we are actually ready to do the test. Yeah, would you put it in to the machine? Do you have the high-tech centralizing device? Yes, good. High-tech. Mm-hmm. And is it turned in? Yeah, you can take it off in this way out. That's perfect. Yes. so. And Johan's set up for the right speed.
Yeah.
Yep. Perfect.
Fast way to make it goes up.
Yeah, I think you can. I don't know if you can.
If I keep it pressed, it will go up, but if maybe there is something faster. It will take like some minutes to go up.
No, apparently not.
No, I don't. Yeah, we have tried once time together,
Yeah.
but there is no way.
It's fixed.
Yeah. Yeah, but that's okay.
Yes, yes.
No, you just have to wait for that to run all the way up, apparently. With the actual load will be shown in the upper display there, and the tendencies of the load and displacement on the two curves. The red one is load. Way! We have load. You would see a little bit of loading in the start, and then it takes off. That's because there's a swiveling head in the top that has to align to the specimen first, and that takes a little bit of loading. When that is aligned with the specimen, then you have the actual loading.
Var det kun til evolutionsmåling nu? Eller var det til køring til brud?
Vi tager ideen er at tage flytningsmålerne af, inden den bryder.
Vi ramte 300 kilo, som vi nærmer os.
Ja. Ja, men det er fiberbeton, så det er formodentlig ikke så dramatisk.
Nej, det er selvfølgelig.
Hverken for jer, der sidder tæt på, eller for måleren.
Den der sikkert lige at skærpe på.
Det mener vi ikke er nødvendigt.
This is more or less the peak.
Yeah.
300 and...
Yeah, it is. You can see here.
Yeah.
It is failing now.
Now you can see it practically.
Yep, that's it.
Okay, so what we want to do, of course, with this data is read load versus the information from these two gauges, which you get the average of in the data file. And then you convert that into stress and strain, right? What's important in that calculation is that you know what is the initial distance between the two blades. Right, because they will tell you a certain deflection in millimeters, but if you don't know what is the initial distance between the two, you cannot calculate strain. Okay, so it would have been important now, or maybe we can measure that at this point. What is the distance between the two measurement points?
But
What is that?
We don't need it.
It already averages, or what?
Yeah, we don't need it because we check the displacement just here, and if I have the bolt, I will do the calibration just with this movement. So I don't need the.
But if you want to get the stress-strain relationship,
Yeah,
what do you do?
I will have the displacement. I have the load, so I can.
Okay, that gives you load displacement.
Yeah.
But if you want to get stress-strain, what do you do?
I have the area of my cylinder.
Yeah. And what do you do to get displacement to strain?
I have the heart of my cylinder.
That's what no, not the cylinder, because just
Okay, yeah.
the distance between the two blades is important, as I just mentioned. Yeah? So you have to measure that. That's quite important, because if you say you measure the displacement over such a distance and it's 1 millimeter, it is much lower of a strain than measuring a millimeter displacement over this type of reference length. Okay, so strain, of course, is delta L over L. So the delta L you get from this device, but the initial L, you need to know that. So quite important. So whenever you run this test, you measure that, you get load versus deformation in terms of newtons and millimeter, and from there you will derive stress strain. That gives you an idea of what is the compressive strength and also what's the modulus. Yeah? We have from this material, the identical material, we have about 15 specimens. So each group, when it's your turn, you come down here, you do 3 tests, and in the end we will compile all the information from these 3 times or 5 times 3 tests, and you have a total of 15 to evaluate then statistically, which should be fine. So you have to share. You do your test and you exchange it with everybody else. Okay? Maybe you have a thing to upload the data or, okay. Holger. Any questions? Okay, simple test, but of course very meaningful, right? You can do a lot with just measuring load and deformation. For structural purposes, that's all you really need to know about concrete. Right? What's FC and what is the strain? Okay? Thank you.